Yeah, I'm sorry. So, joint work with Terra Conde, Stephen Koenig and Koenig-Kuelshammer. Some details are tentative. And it grows out from an attempt to understand a construction from the paper of Koenig-Kuelshammer and Ovsienko. Construction. This is the paper in Advances 2014. So let E be an exact category in Quillian's sense, which is k-linear over a field. And suppose that we are given a family of chosen or distinguished objects Fp in E, indexed by some set P. And all the objects of E are finitely iterated extensions of the objects of P. So E is the extension closure of the set of all objects of P in E. Then, so there will be two theorems. Theorem 1 is that there exists, one can naturally construct a k-linear abelian category B with irreducible objects, irreducible objects Fp, Lp in B, indexed by the same index set. And these are the irreducible objects in the k-linear category in the strongest possible sense of the word. So the homomorphism between them are just k if P is equal to Q and 0 otherwise. And there is an exact k-linear functor lambda from B to E, lambda of Lp is equal to Fp. And the map lambda m pq, the map of the X spaces induced by the functor lambda. These maps are isomorphisms for all PQ in P and n greater or equal to 1. And also, additionally, lambda is surjective on the isomorphism classes of objects. This is the first part of the problem's title, the homomorphism removal. So there is an exact category whose objects are finitely iterated extensions of some distinguished objects, and there can be non-trivial and complicated homomorphisms between the objects of P in E. And all these homomorphisms are removed by the passage from an exact category E to the abelian category B. So the homomorphisms in B are trivial. There's nothing but the multiples of the scalar multiples of the identity morphisms. While the X spaces, so the homomorphisms are removed, but the X spaces don't change. The X spaces for n greater or equal to 1 are the same in B and in the original exact category E. So more precisely, the abelian category B is the category of finite-dimensional comodules over certain coalgebra. Category of finite-dimensional C-comodules, where C is a co-associative co-unital coalgebra. And the maximal semi-simple subcoalgebra, the co-radical, as other people say, of S, denoted by L, it is just the direct sum of the coalgebras K over all the points of the indexing set. This is the maximal semi-simple subcoalgebra. It has this form. So the quotient CSS over L is a Koenig-potent coalgebra without K. Now the homomorphism repackaging problem, homomorphism sorry, thank you. Of course, yes. So we want to define an object, algebraic object, over C containing full information about the exact category E. So we want to repackage the spaces of homes over E from Fp to Fq into an object of a C, so that E could be recovered from it. So I will now define a class of algebraic structures to which our object over C will belong. And these are called semialgebras. Semialgebras over coalgebras over fields. So if you know what a coring is, then the semialgebra is a dual concept. A coring is a coalgebra over an algebra. A semialgebra is an algebra over a coalgebra. So if C is a co-associative co-unital coalgebra, then there is the dual construction to the tensor product of modules over a ring, cotensor product. If you have a right C-comodule and the left C-comodule, then you can construct a vector space which is called the cotensor product. This is traditionally denoted by square. So the cotensor product of N and M over C is the kernel of the map from N tensor over Km. There are two maps from N tensor Km to N tensor Kc tensor Km. So I denote the coaction map by nu. So this is nu tensor identity, nu N. And this is identity tensor nu M. You take the difference of these two maps and take the kernel. This is the cotensor product. So, as usual, the cotensor product of a right comodule and the left comodule is a vector space, but if you consider bicomodules, then the cotensor product of two bicomodules is a bicomodule again. So C bicomod C is a monoidal category. No home finiteness assumptions are. I'm not sure that I understand how to. Thank you. So, category with respect to the cotensor product operation with the unit object, the CC bicomodule C, the unit object of the cotensor product. Oh, I think I realized how to do it.
Yeah, there's no, it doesn't change.
Sorry?
Microphone. Okay.
Is it now better?
Like this, it's better for you.
Thank you.
You're welcome.
A semialgebra is a monoid object in the monoidal category of bicomodules over a coalgebra. Algebra S over C is an associative unital monoid object in C bicommod C. This means that S is a CC bicomodule. There are maps. This is the multiplication map of the monoid, otherwise called the semi-multiplication map. This is the unit map of the monoid, otherwise called the semi-unit map. These are CC bicomodule morphisms. And then there are the usual associativity and unitality axioms. So there are two maps from S cotensor CS, cotensor CS to S cotensor CS. So from the triple to the double cotensor product, there are two maps. M cotensor identity and the identity cotensor M. There is a map M here, and the two compositions are equal to each other. So the semi-associativity, the associativity axiom with the two compositions are equal to each other. And S goes to S cotensor CS in two ways. So there is semi-unit on the left side or on the right side. This goes to S by the same multiplication, and this composition should be equal to the identity of S. Now the category of one-sided C-comodules, left C-comodules we want, is a left module category, over C bicommod C, also with respect to the cotensor product over C. So a left S semi-module is a modular object in C commod over the monoid object S in C by commod C. So this means a left S-semimodule M is a left C-comodule endowed with a semi-action map, and this is a C-comodule morphism, must be C-comodule map. And then there are the usual associativity unitarity equations. Let me not write them here to save time. They are similar to the ones which are up on the blackboard. For the similar diagrams express associativity and unitarity equations for a module over a monoid, in this case a semi-module over a semialgebra. So there is the forgetful, so the category of S semimodules, I denoted by S SI mod. So there is the forgetful functor, the obvious forgetful functor from the category of C-comodules. This functor has a left adjoint, which is given by the cotangent product with S over C, like this. So if M is a C-comodule, then the cotangent product is called the induced S-semimodule. The category of S semimodules is not always abelian. It is so there is an equivalence assertion for when this category is abelian. So it states like that: the category of S semimodules is abelian, and also the forgetful functor from S semimodules to C-comodules is exact. This holds if and only if S is an injective right C-comodule. So S being an injective as a left C-comodule and also injective as a right C-comodule. So both the one-sided comodules being injective it is a reasonable general assumption. General assumption of good behavior. Making S well behaved and the semi-modules. In the context of our construction, the homomorphism repackaging construction, semialgebras satisfying a stronger condition appear, which make them special in some way. A certain restrictive condition is satisfied by the semialgebras appearing in the homomorphism repackaging construction. And this is a certain assumption, if stated in the generality in which I'm stating. The theory here, it is the assumption of bicomodule injectivity. So say, this is the terminology for the talk, it's not commonly accepted, but it doesn't seem to be a good commonly accepted terminology. Say S of special type if E from C to S an injective map, the semi-unit map is injective, and the quotient bicomodule, so S bar, which is S over E of C, is an injective CC bicomodule. This is a restrictive condition. So a bimodule which is free, projective on one side and also projective on the other side is usually not projective as a bimodule, and likewise a bicomodule which is injective on the left and injective on the right is usually not injective as a bicomodule. So this is a restrictive condition. In this case, if this is the case, then the full subcategory of all induced semimodules this is the full subcategory of all semimodules induced from arbitrarily big comodules, the infinite-dimensional comodules. So let me denote it like this: big induced semimodules, and there is this category is important for us. This the category of semimodules induced from finite-dimensional C-comodules. It's the category of small induced semimodules. Both these categories are closed under extensions. In the abelian category of S-semimodules. This holds because the functor on the Ext space, Ext1 spaces induced by the induction functor is surjective. So this, an explanation for this is because the induction functor induces surjective maps on Ext1 between arbitrary comodules. And in fact, it also induces bijective maps X with the numbers greater or equal to 2.
Sorry to interrupt. I see that those two lines, if this is the case, there's no difference between those two cases.
Oh no, take S equal to C, then take S equal to C, then the assertions are of course trivial, but still these are finite-dimensional comodules and these are arbitrary comodules. So theorem 2, this is the homomorphism repackaging. For any exact category E with a set of objects Fp as above, so E is the extension closure of the set of objects Fp, one can construct, if there exists, one can naturally construct a semialgebra S over C. C is the coalgebra from the previous theorem, from theorem 1. And this will be a coalgebra of special type, a semialgebra of special type. In the sense of the definition on this half of the blackboard, such that the category, the exact category E is equivalent as a k-linear exact category to the category of the small category of induced semimodules. So the exact category structure on S mod induced, inherited from the exact category structure, from the abelian exact structure on the abelian category of semimodules. And there is a commutative diagram of exact functors. This is the functor lambda from theorem 1. This is the induction functor. So this construction is a homomorphism repackaging in the following explicit sense. So beyond, in addition to the category E being equivalent to the category of finite-dimensional C-comodules, the category of small induced semimodules from finite-dimensional C-comodules, the quotient S bar, which was defined as S over the image of the semi-unit map, is isomorphic to the cotensor product. I skip some technical details. And U is an L bicomodule. L is the maximal quasi-simple subcoalgebra in C. This is the direct sum of fields over the points in the indexing set. And the category of comodules of such a coalgebra of simple nature is just the Cartesian product of the categories of vector spaces. So L comodules are collections of vector spaces indexed by P, and LL bicomodules are collections of vector spaces indexed by pairs of indices, P and Q from P. So this, as a collection of vector spaces indexed by P of Q, well, this is, let me write it, direct sum of U PQ and U PQ is hom E from FP into FQ modulo K delta BQ. So the whole non-trivial part of the homomorphism spaces between objects between the distinguished objects FP in the exact category E got repackaged into the quotient of S over the semi-unit map. So let me give you some examples which are supposed to convince you that some results like this are at all plausible. So these are degenerate cases, degenerate or borderline cases. So there are two degenerate cases. So first one is assume that X greater or equal to 1 over E in E from FP to FQ vanishes. All the higher X spaces between the objects FP vanish in the exact category E. Then all the X1 spaces vanish in E. So then E is a split exact category. So the coalgebra C is semi-simple in this case. For semi-simple. So C is equal to L. The most simply constructed coalgebra. So for a coalgebra of this form, semialgebras over L, well, they are first of all bicomodules. So a semialgebra is a bicomodule. And here is a formula for what L bicomodules are. They are pairs of, they are vectors, the collections of vector spaces indexed by pairs of indices from P. So semialgebras are multiplication structures on such collections of vector spaces. These are rings, K-algebras with P objects, multi-object algebras. And these are the same things as K-linear categories R with the set of objects of R equal to P. These are, in this trivial borderline case, these are my semialgebras. And with the category, given a category E, I consider the K-linear category on all the full subcategory on all the objects of P. This is a full subcategory in E, and I take the opposite category because I consider left modules. So this is opposite to the full subcategory on Fp in E. And then E is recovered as the category of finitely generated free left arm modules. Yeah, so returning to the question asked by Bernard, this example is supposed to convince you in particular that there are no finiteness assumptions. So all the home spaces can be infinite dimensional. The semialgebras take care of that. What the? Oh, coalgebra. Take K. The ground field K is a coalgebra. Take direct sum of these coalgebras. This is like yeah. And the second degenerate case is the opposite one. When hom E from Fp to Fq is K delta Pq. So when the homomorphisms are trivial, there is nothing to remove and nothing to repackage. So you come back to the same category, but this is it's a non-trivial and interesting assertion that the category is abelian in this case. So generally, if E is the set of finitely extension closure, the set of finitely iterated extensions, closure of P, P and P, and hom E from Fp to Fq is 0 for P not equal to Q, and a division ring as Q field for P equal to Q. Then, so if you have an exact category like this, then such an exact category is always abelian. Then the exact category is abelian with the abelian exact structure. And moreover, if in the situation at hand, if E is K-linear and hom E from Fp to Fq is K delta Pq, then E is the category of comodules, or the category of finite-dimensional comodules over a coalgebra whose semi-simple part is the direct sum of fields over P. So once again, C, the coalgebra C can be infinite dimensional. So maybe I should let this go up and bring that one down. So I don't have that much time left, so let me very briefly sketch some ideas of the proof. Of both the theorems so it starts with a theorem of Bernard Keller's, which is more general, but let me state it in the situation I'm interested in. So for any E and Fp as in our context, there exists a digi category A whose set of objects is P, and this digi category represents X star E from Fp to Fq. So the complex of morphism in A from P to Q is computing these X spaces, so such that the bounded derived category of E is equivalent to the triangulated subcategory generated by free digimodules with ungenerated free digimodules with one generator over A. Let me say in the derived category of A modules. So the object Fp in here goes to the free digimodule with one generator sitting at P. Oh. We want to replace the digi category with a minimal strictly unital A infinity category. So let me perhaps skip the definition of an A infinity category and strictly unital A infinity category. So minimal means that D, let me denote this minimal strictly unital A infinity category by A bar. And D A bar, which is M1, A bar is 0. And there is a theorem of Koenig-Kuelshammer-Ovsienko and Koenig-Kuelshammer-Ovsienko. So as I understand, Koenig-Kuelshammer did the non-unital A infinity category case, and in the dissertation of Lefebvre, the strictly unital case was worked out. Any strictly unital A infinity category A is strictly unitary. A infinity are quasi-isomorphic to a minimal one. Strictly unital as well as non-strictly non-unital, A infinity category quasi-isomorphisms are invertible, so there are quasi-isomorphisms quasi-invertible. So there are always quasi-isomorphisms going in both directions. In this case, so one doesn't need to specify that. Now, there is another, unfortunately, less popular definition, which I also don't want to spell out now for lack of time. So let me just give you a hint. Curved DG algebras are sort of like infinity algebras. But instead of M1 is the differential, M2 is the non-associative, homotopy associative multiplication, M3, M4. So instead of a sequence of operations like this, a CDG, a curved DG algebra has a sequence of operations M0, M1, and M2, and that's all. So M2 is a map from K to B2, is an element in B2, called the curvature element. M1 is the differential, M2 is just the usual associative multiplication. So, thank you. So, M2 is an associative multiplication, and M1 is a differential which doesn't square to 0. So, let me leave it at that. Now, non-unital A-infinity algebras are and also A-infinity categories are described by DG coalgebra structures on co-frequent potent or cotensor or tensor coalgebras. Strictly unital A-infinity algebra structures are similarly described by curved DG coalgebras. So non-unital A-infinity category A bar is the same thing as a, so it will be precise, co-augmented DG coalgebra structure on the cotensor coalgebra. This is upside down T for tensor or cotensor. So L plus A bar plus A bar is a collection of A bar PQ, so it makes it a bicomodule over L, and I write the cotensor product here. This is called bar construction or Koszul duality or something. So similarly, strictly unital A infinity categories A bar, and there is non-degeneracy assumption. The unit element should be non-zero for construction to work with 1p not equal to 0 for every p in p. I should have said, so it is the cotensor coalgebra on this bimodule of L.
On the left of the equality sign. On the left of the equality sign, you just go coalgebra.
Cotensor.
Line number 3.
1, 2, 3. On the left of the equality sign, T. What?
T of what?
Okay, TL of A bar. Sorry, thank you for the question. Yeah, this is a bit tentative, not only because some details are not understood yet, but also because so insert everywhere in the formulations of the theorems the very important basic assumption that Fp is not equal to 0 in E for every P in P. I don't know why I forgot to say that. Strictly unital infinity categories A bar with non-zero unit elements correspond to co-augmented CDG coalgebra structures on TL of A bar over L equal to direct sum. L is just the collection of all the units. L is embeds into A bar as the collection of the unit elements. So A bar over L yeah, so maybe I should open this, or hint at opening this parenthesis again, and say that there is a certain total grading on the cotensor coalgebra, and the total grading is the grading induced by the grading of A bar minus the grading by the number of the tensor factors in here. Total grading is A bar grading minus tensor grading. And for this reason, one sometimes puts A bar of 1 here. And likewise, one sometimes puts A bar of 1 here to indicate the grading shift. Okay. Okay, returning to the situation at hand. So, at hand, in the situation at hand, A bar n is equal to 0 for all n greater than 0. And it is important that with A bar, if A bar is the minimal strictly unital A infinity algebra, A infinity category associated with the Ext algebra of the objects of P in E, then we have this, and we certainly have D A bar 0 from A0 to A1 vanish. These conditions are important. The rest of the minimality conditions are not so important. I consider A bar greater than 0. This is the strictly unital A infinity subcategory in A bar with the 0 component is only the trivial morphisms, only A. So this is K delta PQ. All the other components stay the same. So I drop all the components in A bar representing the homomorphisms and keep only the ones representing the high X. One can easily see that this is a strictly unital A infinity subcategory. Now I have yes? I am running over time. So let me say that Q is the tensor coalgebra of A bar over A1. This contains D, which is the tensor coalgebra of A bar greater than 0 over A of 1. This contains, this sits in Dn is equal to 0 for all n less than 0. This contains C, which is H0 of D. And this contains K, which is the maximal differential subcoalgebra in Q concentrated in n in degrees less or equal to 0. So the claims, so C is contained in D and in K and D are contained in Q, and the claims, the vertical inclusions are weak equivalences. This is a weak equivalence of CDG coalgebras. This is a weak equivalence of DG coalgebras Now I sort of explained the idea of the proof of theorem 1. This, you take a bar greater than 0, the subcoalgebra with the homomorphisms, infinity subcategory with homomorphisms dropped. You take the bar construction and take the H0. This is the coalgebra C, and it's claimed that this passage to the degree 0 cohomology doesn't change the weak equivalence class. And let me say that S is the relative Koszul dual to K over C. Okay, I should stop here, I think. What's FP? Well, E, yes, E is, but I mean, in my datum, I don't have only E, I also have objects of P. What do you want to take as the objects of P?
Yeah, I take a finite-dimensional algebra A.
Yes.
I take the finite-dimensional module over this A.
Yes.
This is the abelian category, which is E.
What is FP?
P is
FP.
simple module.
Well, simple models. Okay. Then you assuming that these models are absolutely simple, so the endomorphisms are K, you get the coalgebra C dual, vector space dual to algebra A.
And then coalgebra A.
Yes.
That's what I want.
So I thank you for your talk.
Good afternoon to everybody. I'm Dominique Moina, Deputy Director of the Institute, Henri Poincaré, YHP. So the Institute, through me, is very happy to welcome you for this nice program, Higher Structures in Geometry and Mathematical Physics, and in particular, in this workshop, Homotopy Algebra and Higher Structures. I would like to say some word about this institute for those who are not well aware of the various missions of this place. First, as you know, the YHP hosts scientific exchange at the international level in mathematics and also in theoretical physics. The Centre Émile Borel is a department dedicated to the organization of these various programs. Second, the IHP is endowed with a precious library which preserves, develops, and makes available to the institute visitors a large collection in mathematics, theoretical physics, and also history and philosophy of science. Third, more recently, the institute has engaged in outreach activities in the popularization of mathematics. The Maison Poincaré is a new department in charge of coordinating these activities. This will materialize soon through the opening of a museum in the building opposite Perrin, in memory of Jean Perrin, who was working there. Finally, the IHP is a welcoming home for various seminars, meetings from either the National Committee of Mathematics and Theoretical Physics or scientific foundation and associations. So finally, the staff of the Institute, Sylvie Benzoni, Director of the Institute, Aurore Marcos, General Secretary, and myself for the direction, Marco Perez and Alessandre Duplessis for the techniques, Sylvie Dubois, Patricia Raboteur, Florence Lajoigny, and Eric Chaffard for the logistics, Jeff Renaudat and Yves Dapra for computing science, and finally, Elodie Destrebec and Anne-Marie Landes for Financial Center will best meet your demand. So have a good stay in Paris and a fruitful meeting here. Thank you.